On the surface of pretty much every high-performance part you can think of, we're talking jet engines, surgical implants, you name it, there's a hidden story. It's a story of incredible stress and intense heat. And today, we're going to learn how to read it.
So, let me ask you this. What could a jet engine blade, which operates at thousands of degrees, possibly have in common with a surgical hip implant that has to work perfectly inside a human body for decades? I mean, they seem like they're from totally different worlds, but they share a really crucial secret.
And it all comes down to this. Their success isn't just about being shiny or smooth. It's actually determined by an outer layer, thinner than a human hair, that dictates how long they'll last under some of the most extreme pressure imaginable. Welcome to the world of surface integrity.
I love this analogy. Surface integrity is basically the invisible DNA of a part's surface. It's not just the texture you can see or feel. It's the hidden code of stresses, microscopic cracks, and chemical changes left over from manufacturing that pretty much dictates its entire future performance.
So, to understand how engineers control this invisible DNA, we're going to explore the 4 fundamental levers they have to pull: the cut, the tool, the coolant, and, of course, the material itself.
All right, our first lever is the most intuitive one: how the material is physically cut. Machinists are constantly tuning 3 main dials: cutting speed, feed rate, and depth of cut. And believe me, their interplay is a very, very delicate dance.
It's this constant balancing act, right? Research from people like Dimmer Palat shows that cranking up the cutting speed can actually create a smoother surface. But, and this is a big but, if you push the feed rate, that's how fast the tool is moving across the material, too high, well, the finish gets rougher. It's all about finding that absolute sweet spot, that perfect recipe for each job.
Now here's where it gets really fascinating. A faster cut can actually make a part stronger. Yeah, you heard that right. As this study found, hitting a specific high speed actually squeezes the surface layer, creating something called compressive residual stress. Just think of it like a built-in force field that actively pushes back against cracks. It makes the surface way more durable.
But the speed of the cut is only half the story. Our second lever is the tool itself. See, it's not just how you cut, it's what you cut with. And the secret weapon of these incredible high-tech tools, it's often their coating.
Modern cutting tools are almost never just bare metal. Oh no, they're covered in these incredibly thin, super hard coatings like titanium aluminum nitride or chromium nickel tungsten. This stuff acts like armor. It slashes friction, shrugs off intense heat, and ultimately leads to a much more stable, controlled cut that doesn't damage the surface of the workpiece.
And some of these coatings do more than just act as armor. For instance, research from the Reshev University of Technology shows that a specialized TIBW coating actually acts like a heat sink. Its unique structure has amazing thermal conductivity, which allows it to actively pull damaging heat away from the part's surface during the cut. This is huge because it prevents the heat from ruining the material's internal structure, preserving its integrity.
And that brings us perfectly to our third lever, managing the insane environment of the cut itself. Machining generates a staggering amount of heat and friction, and if you don't control it, you'll completely destroy the very surface you're trying to perfect. And that's the job of coolants and lubricants.
Let's just look at the 2 extremes to see what a difference this makes. On one hand, you could machine completely dry, no coolant at all. Sure, it's cheaper, but it leads to scorching hot temperatures that can absolutely ruin the surface. On the other end of the spectrum, you have cryogenic cooling. This blasts the cutting zone with something like liquid CO2, super chilling the area to minimize thermal damage and friction.
And the data just makes it crystal clear. Based on findings from Zhao and their colleagues, when you're machining a really tough titanium alloy, dry machining creates the roughest surface. No surprise there. Using something called MQL, that's minimum quantity lubrication, kind of like a fine mist of coolant, is better. But look at that cryogenic cooling. It creates the smoothest, highest quality surface by a huge margin.
Okay, so we've got the cut, the tool, and the coolant. But our final lever is one that starts long before any machining even begins, the material itself. The quality of that final surface depends so much on the material's condition and its history before a cutting tool ever even touches it.
A part's journey often includes a critical step before machining, and that's heat treatment. You can kind of think of this as a workout for the metal. By carefully heating and cooling it, engineers can toughen up its internal grain structure. This makes it stronger and way better prepared to handle the stresses of both the machining process and its final job. Hey, remember that protective force field we were talking about earlier?
the one created by high-speed cutting? Well, heat treatment is another major way to build that beneficial state, that compressive residual stress, into the material from the very beginning. As research by Holmberg shows, this preloads the part with protective forces, giving it a massive head start and resisting cracks and failure down the line.
So, here it is. Here's the crucial point. Creating a perfect, high-integrity surface isn't about pulling just one of these levers to the max. It's about a sophisticated, interconnected dance between all four. You need the right cutting parameters paired with an advanced tool coating, supported by an optimal cooling strategy, all applied to a material that has been properly prepared. That is the recipe for success.
So the next time you see the landing gear on a plane, or maybe even the tools in an operating room, I want you to remember this. Their real strength isn't just skin deep. It's written in the invisible language of their surface. What's its story?